basically the success of any high-speed civil transport program depends upon minimization of its environmental impact. Foremost among these, as we have seen yesterday from several speakers, are the forward propagated fan noise, which is second only to the jet noise in component. And this becomes much more severe when you consider supersonic inlets, which have supports and bifurcations, and also the fact that such inlets are optimized for cruise conditions, so you need auxiliary doors at landing and takeoff for improving the inlet area. So, and this has been studied by several people in the past, notably by Trefny and Weserbar, Woodward, Wenger, in addition to several other experimental studies. So the objective of this exercise was to determine the effect of forward flight on high-speed fan noise using 2D bifurcated inlet designed by Boeing, and compare it against baseline data, which was a conventional takeoff and landing inlet, which was also tested earlier at Virginia Tech. So the experimental conditions chosen were for landing and takeoff corresponding to 50,000 and 70,000 RPM, which was, I'll come to the model details in a moment. 60% of the simulators corrected design speed and 88% respectively. So the blade passage frequencies on the simulator for these conditions corresponded to 15 and 21 kilohertz. So, and it was run at 60 meters per second, corresponding to like a Mach number of 0.2, and this frequency range. Come to the loading in a moment. The tests were carried out at FMRL's anechoic chamber, which was made to a closed circuit wind tunnel in order to produce an open jet anechoic chamber facility. And the model was a turbofan simulator, a picture of which you'll see next, made by Tech Development Model 460, which was simulated GT90 turbofan. And it was hung in the anechoic chamber, which was about 2¼ meter cube at about 1½ meter from the roof. So it was in the center line of this open jet. Two conditions were simulated, both the static and the forward flight. And for the static conditions, the entry and the exit were boarded off and covered with anechoic foam, and the jet exhaust went through a pipe duct into the tunnel for the static case. So the microphone measurements were made in an hour, 1.2 meters away from the inlet leading edge. And this distance was arrived by the fact that you took the acoustic wave number based on the blade passing frequency times the diameter of the inlet should be much greater than 1. So it's in the acoustic far field. And measurements were made from 20 to 110 degrees. We could not come in line with the inlet because during the on-flow conditions there froze and interference. For any case wherein you have forward flight, there needs to be a correction made. So this should be theta prime, sorry. And this has been documented incredibly in a work of 98. And this takes into account the forward flight Mach number and the angle at which it's been done. So this gives you the details of the simulator which was used in order to simulate the engine acoustic spectra. This was, like I said, a Model 460 simulator based on a GT90 turbofan engine. This about 10 centimeters in diameter, which was driven by a single stage turbine which ran on compressed air at 300 psi. It had a max speed of 80,000 RPM possible, and we ran it at 60 and 88% of that, like we recall, for the landing and takeoff conditions. It had 18 blades on the fan, and 26 sterile vanes. Reynolds number based on tip speed was about 1.7 million for the higher RPM case. The tip speeds were like 260 and 380 meters per second approximately for the landing and takeoff case. So one was subsonic, one was supersonic. In order to get the acoustic spectra, it's important to simulate the blade loading accurately. For the fan stagnation pressure ratio for this was calculated to be 1.38, the pressure ratio across the fan at 70,000 RPM. And this was achieved by means of a choke plate, which had a 0.3 square meter hole placed at the end of the exhaust, which would assure us of the proper pressure drop of the fan. This is a close-up of the test facility, and you can see here the anechoic chamber mated to the closed-circuit wind tunnel, and here simulator with the 2D bifurcated inlet mounted on it. There was also a conventional inlet, which you'll see soon, for comparison. This is the microphone and its traverse, and microphone could be moved in a 2D plane as well as rotated angle towards the inlet at all times. The microphones used were of the type 4135 of BNK, and could do a maximum of 100 kilohertz. 200 kilohertz was sampling speed. This is a conventional inlet with flat plate inlet guide vanes, 14 of them, and a stationary nose cone, and there's no bell mouth on this, which is the only difference we had between this and the test carried out at Virginia Tech. This was to facilitate a comparison of our facility. We show the details of the bifurcated inlet for this case, and it had 16 of these guide vanes, and no auxiliary doors were used in this exercise. It shows here the wind tunnel background noise spectra. The wind tunnel fan ran at 1800 RPM, so you can see up to kilohertz the frequencies of the BPFs of the fan and its tones. For the overall sound pressure level, that's why for integration only frequencies beyond 1 kilohertz were integrated to obtain that. And at all times, the fan spectra was more than 10 dB below that of the engine spectra. This shows a typical fan spectra at an angle of 60 degrees, and this is for the 60% case, corresponding to a blade passage frequency of 15 kilohertz, which you can clearly make out in the peaks. And this is a first comparison between the studies carried out at Florida State versus those done earlier at Virginia Tech. This on a conventional inlet, and the dotted line shows the studies at Virginia Tech, and which are limited to a maximum of 25 kilohertz. In their study, we can go all the way to 100 kilohertz. Only 50 is shown here because it's how much interest beyond the point. And you can see it matches fairly well at this point. When you see the integrated sound pressure level, you see a slight 1 dB difference at the higher speed, higher RPM, as opposed to this, and this is attributed due to the fact that they had a bell mouth on their inlet, and the presence of the bell mouth seems to affect the results only at the higher speed, not at the lower one. This is the case for landing, and this for takeoff. The angular variation of the sound pressure. This shows the spectra for forward flight for conventional inlet at 70,000 RPM, and this is again compared with the Virginia Tech results, and they show this at 88% of the design speed. Since the tip speed is supersonic, we see a lot of combination tones, which are pretty comparable to the BPFs of the fan itself. And this shows the comparison against the static and for forward flight, and we can see in the presence of forward flight, there's significant lowering of both tones and the BPFs for this case. This shows the landing case, which is much lower, and as a reference, the tunnel spectra is also plotted on that. You can see it's well below area of interest, and we can see that in both cases, the static is much higher, more than 7-8 dB compared to the forward flight cases in here. So having established the baseline, and this shows the directivity of the BPF. So this shows that most of the reduction is coming from the reduction of the BPF and its harmonics. So we can see the significant drop in the BPF when you go to forward flight speeds. This shows for the conventional inlet the angular variation of the overall sound pressure level for the landing and the takeoff cases. We can see it's not there's not much of a difference in the landing case, but it's only more for the takeoff at the higher RPM case. You can also note here that for the landing case seems to actually increase. This is because of the fact that in the static case, the exhaust was piped out through the end termination of the anechoic chamber, whereas in the forward flight case, the exhaust was let out with the flow. So as you progress towards the rear end of the simulator, the jet noise would come into play. At the higher speeds, we can see a significant drop, about 5 dB at all angles. And this is attributed to the fact that for forward flight, the tip speeds would reduce. And secondly, the inlet distortions also reduce, leading to lower turbulence levels for the inlet. This shows the directivity plot is a bit cluttered, but it's basically saying the same things, that if you compare the landing, the circles, and the forward flight, we see significant decreases, and it basically is the same message, that the decreases are coming from the reduction in the tones. So having established that, I'll quickly show the similar results for the 2D inlet, and again this is the tunnel background, and we can see in here for the landing case, this is the lower RPM, we see the static, that's no forward flight by the dotted line, and for forward flight, that's at Mach 0.2. And we can see similar decreases in the BPFs and subharmonics and harmonics. However, one of the things fairly obvious, that the decrease is more, unlike in the CTOL inlet, where the decrease was only for the takeoff case. Here the decrease is quite a bit in both the takeoff and the landing case. We'll come to that in a minute. And this for the takeoff case, and we can see a significant decrease from the static conditions when you go to forward flight at the same angle. If you look at the overall sound pressure levels and their angular variation, the same conclusion is reflected in them, that there's a corresponding decrease at all angles for both landing and takeoff cases. And like before, the jet noise is seen to be dominant at the landing case. We do not, while we see an increase, we do not see the jet noise exceeding the baseline, simply because the levels are so much higher of the fan, or of the simulator fan itself. To conclude, the forward flight results in a significant reduction in overall sound pressure level, and an amplitude reduction of the blade passage frequency and its harmonics. And the greater reduction in takeoff case, especially on the Boeing inlet, is due to reduction of the relative velocity of the blade tip, avoiding the reduction in the inlet flow distortion and avoiding the tip flow separation in such inlets, which has been documented by earlier studies. Thank you.
Any questions? I want to make a note here, and I don't think Farooq is here. This is the engine where Farooq's finger got cut. I don't know, most of you may not know, Farooq lost his finger on the left-hand side. We had a problem. I asked him to go into the chamber and see the flow is coming smoothly into the inlet. And Farooq, being Farooq, instead of using a tuft,
Use this finger.
he was put his hand in front of it. And luckily, because he was doing this, he was doing his finger is going like this, and it sucked the whole hand into it, and his finger is cut right here. And most of you don't notice it because there's plastic on it. So this experiment,
It's a traumatic experience.
and I have never renewed the contract. I have no desire to do it anymore, because this is a very dangerous experiment to do in the lab, because it's in a confined environment. It runs at 70,000 RPM, and it is a mess. So anyway, you don't see a lot more details in here because I switched him off to water injection after this experiment.
What's the difference between the two inlets?
One was conventional.
Inlet, like the usual flat plate IGVs. The second was a 2D bifurcated inlet, which is designed for supersonic operation, optimized for cruise conditions, with auxiliary doors.
Do you have an explanation why you have so many rotors, engine ornaments in your spectrum?
At the higher RPMs, you get combination tolerance because the tip speed is supersonic. So you get combination tones with the waves. Which is not present in the lower speeds, or with for flight when the relative speed comes down.